The topic for today's presentation is about the floodwatering system that TasWater has developed over the last 3 years. I'm TasWater's Dam Safety Manager, and Fiona and myself will run through and talk about the journey that we have taken regarding the development and implementation of the system. I'll provide information from the owner's perspective, and Fiona will shine a light on the challenges that she's encountered as the consultant for this particular work. TasWater commenced operation approximately 6 years ago in July of 2013. The organisation was an amalgamation of 3 water and sewerage corporations: Ben Lomond, Cradle Mountain and Southern Water. From our commencement, we've been owned by Tasmania's 29 councils, and more recently the state government became a shareholder in early 2019. In regards to the size of the business and to get an idea of the magnitude that we're dealing with, TasWater has a turnover in excess of $300 million per year, total number of assets exceeding $2 billion, in the order of 200,000 water connections, 176,000 sewerage connections, and we employ in the order of 9,000 staff. In regards to this subject though, and that's about FEWS, that's our flood early warning system. Other relevant information includes the number of dams that we have in our portfolio, which is 300, and they are statewide and include dams on Flinders and King Island as well. Our dams are used for water supply, sewerage and reuse. We have water supply dams that are either on-stream or off-stream or a combination of both. We have 50-odd dams having a consequence category of significant and above and ranging to extreme. Most of our dams in our portfolio are of the embankment type. We also have a number of concrete, slab and buttress dams, plus a few concrete gravity dams. From a regulatory perspective, we manage our dam portfolio in accordance with the Water Management Act of 1999 and its associated regulations and reference to the ANCOL guidelines. Many of our dams have inadequate spillway capacity, and we are currently going through an extensive upgrade program, and in the coming years we expect to upgrade 8 of our larger dams. The development of the flood warning system commenced in early 2016. The requirement for having a system became obvious as we needed to have greater visualisation on how our dams were being operated, particularly during flood conditions. Up until this stage, we had limited real-time data and relied on a spreadsheet system in forecasting reservoir responses to rainfall events. In June 2016, the state was hit by a large easterly storm event, and this storm extended across the breadth of the state, the result of which was severe flooding and extensive damage. Like other dam owners, we had many dams that were affected by the flood, and this incident confirmed for us the need for an integrated flood warning system. The dynamic nature of large rainfall events, like that occurred in 2016, showed that it was not possible to have sufficient resources to be constantly updating our old way of doing things and obtaining data simultaneously. So we learned a lot from the floods of 2016, and from those learnings we applied that to what we needed for our flood warning system. We wanted to be able to input data from various sources that included the BOM, their forecasts, real-time weather data and other dam monitoring information. We wanted to understand what effects our outlets would have on reservoir levels and when they should be operated before, during and after storm events. The platform needed to be intuitive with good visual representation across our whole dam portfolio. The system needed to be used on our operational dams and also to be a key tool in monitoring and managing reservoir levels during our upgrade program. And the system needed to be operated by a small team. We're only a team of 5 or 6, and we're spread right across the state of Tassie. So I'll hand it over to you.
Thanks, Fraser. So I guess that was sort of the brief for us coming into this. So in talking to TasWater, we obviously took all those considerations into our thinking about what sort of system we needed to provide. So we came into it knowing that we had to collate data from a whole lot of different data sources. We also wanted the application to be able to schedule and execute catchment and storage models automatically so that the TasWater operators didn't have to sit there running models. A user-friendly interface. Archiving of forecasts was really important as well, so that all the information that was available when a decision was made could be pulled back up to investigate. Alerting for the operators, and we also needed a proven track record. So we ended up going with a system that was based in software called Delft Fuse, which is flood early warning system, and that's used by the Bureau of Meteorology, SEQ Water, Melbourne Water, and around the world, as you can see on that, by some large water authorities. So it had a track record of being able to be used for flood warning. So one of the considerations in this, we wanted to build a catchment model for each of our dam catchments, where we wanted to be able to estimate the inflow to the storage. So our consideration there was really to be able to have something that was automated, that automatically took rainfall forecasts in and took in observed rainfall, turned that into inflows to a storage, and that it didn't require expert input during a flood event. So what we can see there is really a visual representation of what the model does. Precipitation comes in, evaporation goes out, and your soil stores fill up, some goes down to groundwater, and the rest is running off. So that model gives us inflow into our dams. We then needed a reservoir model as well. So our considerations for that were that it had to be able to obviously simulate everything going on in the reservoir. We had to be able to include spillway operation, valve operation. We also want to include optimisation so that the model could automatically predict a valve operation that would keep the dam safe if possible. Oh, so that's back to Fraser, I think.
Oh, okay. Okay, thanks for that. Okay, so the way we went about this project was to pick a trial location, and the dam that we chose a couple of years ago was the Isandula Dam, which is located in the north of the state. This dam is used to supply Ulverstone, and it has the following characteristics. It's a consequence category, it's a high B. It's a reasonably high dam, 15 metres in height. It's concrete face rockfill construction. The storage volume is around 700 megalitres. The catchment response is really quite quickly. It's measured in hours. And the catchment area is around 30 square kilometres. We also have a remotely operated dewatering outlet on the dam, however it has relatively small capacity. And in this particular instance, we needed to be able to balance water supply against the dam safety risk. Our aim was to forecast the effects of extreme weather events and to also manage small events by introducing sufficient airspace within the reservoir and limit the extent of spill. The system model that was developed and spoken about by Fiona a few moments ago considered the dam's outlet, and the outlet's operation was optimised so that we would not exceed allowable thresholds. The main input to the system has obviously come from the BOM, and the forecast that they provide us with three different scenarios, a 10, a 25 and 50 percentile exceedance probabilities. What we've found since we've implemented the system over the last 12 months is that most of the weather that we're getting obviously comes from the west, and the 50 and 25 percentile rainfall forecasts have been the most representative. However, when we choose these representative scenarios, a bit of engineering judgment is required because it does give us some variation, and we're currently working on the operational rules. However, so far to date, for our trial site at Isandula, the fuse system that we are using has been quite successful. So I'll let Fiona talk more about the model.
All right. I think we'll covered that one. Okay, so one of the challenges in this was really integrating all the data into the system. So even with the pilot system, we had to design a system that was obviously expandable statewide, so we needed to have everything in place that we could then just plug extra sensors into that. So we had data coming in from a number of different sources. We had the Bureau of Meteorology's rainfall forecasts and observed rainfall data. We had data provided, some flow data, which was provided by the Intura system, which is ADMS through a satellite phone. And then we had TasWater SCADA. And the TasWater SCADA system is currently being upgraded and is quite a long way through that. And so this project integrated with that, and now data is coming into PI Historian from the SCADA system. It's coming in through a data bridge also into there, and we're getting the BOM data coming in through a secure FTP site. So all that data is now visible to the flood early warning system. Actually, I'll skip through to that side to start with in a different order. So this is what we get out of the flood early warning system. On the top here, this is a rainfall forecast. So now times this vertical line, this is observed sites in the area, and this is the forecast rainfall. And as Fraser said, we've got 3 forecasts of 50, 25 and 10% oil exceedance. So this is looking 7 days into the future as to how much rainfall we're going to get. So it then goes through our catchment model and forecasts inflows to our storage down here. And if I go back, yep, okay, and so we then take those inflows and run them through the storage model. And we can see from that, hopefully you can see this faint trace up here actually goes over an alert threshold for this event. So we're getting some spill coming out of the storage, that's lake level. Then our bottom one down here is valve operation, so it's saying how much water's coming out through the valve, which is 0 in this case. So this is a valve off case. If we then run that with the model optimising, the model will then predict how far open we need the valve to be, what sort of flow we need to get out of that to keep all the traces then below the critical lake level. So we're trying to keep as much water as we can in storage, but keep the dam safe. So there's additional information available to support decision making, and that includes things like Bureau flood warnings, so we're also bringing that into the system, radar information and other observed rainfalls and flows from around the area. So we can see here a screen showing the forecast rainfall data in a visual way, which you can then step through as the event comes through. And radar data, and you can see here there's Isandula Dam and there's a warning that that needs looking at. There could be a flood coming. And that's just zooming in on that one. So stage 2, that was stage 1, as Fraser said. The pilot stage, stage 2, we now have expanded that to more dams and larger area of the state. So we have additional SCADA data coming in now and underway to get southern reservoirs in as well. We have additional rain gauges coming in, and we'll shortly have other rain gauges through a data sharing agreement, as you can see in grey there. We have other storages now in the system. And for some of the catchments that are still critical but we don't have storage models for, we have a rainfall alerting, which is just based on comparing the observed rainfall and the forecast rainfall to design rainfalls, like a 1 in 2, 1 in 100, and alerts are set up based on these rainfall thresholds. Back to Fraser.
Okay. Thanks for that, Fiona. So to summarise where we've got to, so what we set out initially to do to develop a flood forecasting system, we've largely achieved that. Some additional comments and learnings along the way. We've gained a significant understanding in estimating the effects of rainfall events before they occur, which is critical for us. Rainfall by its nature is difficult to forecast precisely, and this uncertainty should be factored into any forecasting system. In our case, we have relatively small catchments and quick response times. A flood warning system is only one of many tools that should be used when managing flood events, and it's very important to have a comprehensive incident and emergency management system in place as well. The system Fuse has been extremely valuable in us being able to interrogate a number of hydrological inputs that include the BOM and others. Balancing forecast rain uncertainty has been challenging when recommending preemptive releases, as there's usually a tension that exists between the dam safety requirements and for operational needs. The Fuse system has been found to be relatively easy to use and a vast improvement on what we've been using in the past. The trial location at Isandula has demonstrated that Fuse is particularly efficient and flexible, particularly when operating reservoirs in flood events. And the way that we approached it, with starting with a proof of concept and a trial location, has worked well for us. And as Fiona has said, those learnings are critical into the next stage of the final system that will include all our major dams and catchments. And that's all. Thank you.
Thank you. Do we have any questions for Fraser or Fiona? Royce?
I recall in the 2016 floods there was challenges at Isandula with connectivity and getting a signal to the phone, and we had to send guys in and out to get signal. Did you find those challenges?
Yeah, those challenges are pretty common throughout the system, but at Isandula, since the floods there, we've had an upgrade to the telemetry. So that is a part of this process as well, to make sure that our telemetry is now reliable and providing us the data we need.
Thank you, a great presentation. Has the calibration of the model been improved through referencing your forecasts and then backtracking those forecasts against model parameters?
Not yet, but that is a next stage. So yeah, first stage was getting the system there, and we actually didn't have much data, to be honest, to calibrate the models on to start with, and the SCADA and the flow sites have since gone in, so we will now have more data, and we will definitely revisit that, yes.
I had one more question, and that was whether or not you were actually using the BOM radar imagery in your processing.
We're not yet, but it is capable of taking that in, because they're now providing some feeds from that which actually convert that into rainfall amounts on the ground. So again, this is future work, yeah. So yeah.
Yeah, thanks for the presentation. Great. I noticed that you take information from Ventura, I'm assuming hydro, I guess, as well. Does the information that you gather feed back to them so that they can, I don't know, help their models and control their dams better as well?
No, not at this stage. No, but we have a program of actually, or currently, sourcing data from many different fields or many different other organisations as well. So.
I do have one question, selfishly. Have you guys considered, obviously TasWater has sewage treatment lagoons as dams, incorporating inflow and outflow meters from the SCADA system to predict likelihood of overflow of those lagoons into receiving environments?
In relation to the fuse system you're talking about?
Yeah, this is heavily focused on water supply security and the likes.
Yeah, Fuse has the capability to do that sort of stuff. And in the later slides that Fiona showed, with the 1-in-1s, 1-in-2, 1-in-100-year events,
Yep.
that's where that sort of information would be really quite handy. And the capability of Fuse is that all we have to do is locate those sites within Fuse, and then it would spit out a report if a storm or something that's coming, and it would highlight the high-risk locations. So it's a pretty easy step to take.
Yeah, cool. That's great. I've got one more question after that.
Mike, I was just interested in comparing time to establish the model. It looks all fantastic. Compared to the time to actually get the model working, can you comment on how much time was required to actually get clean data so that the networks were right and everything actually worked when it went in there?
Yeah, it's always the challenge, is getting clean data. That took quite a while, and in a lot of cases there wasn't a lot of data, to be honest. So we were often calibrating models on nearby catchments where there was good data, so we knew where there was good data. So as we were saying, in the future, now that we've got the sites in, we'll go back and revisit those calibrations. So, yep.
Great. Could you all thank Fraser and Fiona, please?